get started. The goal of today's session is to provide basic knowledge and understanding of automotive transients that can occur in a 12-volt vehicle system. In the first section, we'll provide an overview of typical automotive transients. Then we'll take a closer look at several common transient conditions that are accounted for in most system designs, including cold and warm crank, reverse battery, and load dump. And finally, we'll summarize the key items that were discussed. A typical automotive module must account for many transient conditions that can occur on the vehicle power bus. Several transient conditions are very critical in terms of energy and possible stress on vehicle electronic systems. Load dump, for example, has the highest energy pulse. Jump start, although a lower peak voltage than load dump, can put twice the normal voltage on the module supply for an extended time. Negative voltage events can also occur, such as reverse battery condition, and alternator field decay can also create negative voltages at each turn off. Other conditions, such as cold crank and warm crank transients and alternator noise, must also be dealt with so that the vehicle will continue proper operation when they occur. Let's look at more of the details for the transient waveforms just mentioned. For load dump, the peak voltage can reach as high as 120 volts in some systems. This high energy condition, which can last as long as 400 milliseconds, can generate as much as 10 joules of energy. While this condition doesn't occur very often, it is significant and must be accounted for. Double battery conditions can occur whenever a vehicle is jump started. While this doesn't normally happen very often, it can occur at least a few times in the life of the vehicle. A double battery condition will place about 24 volts on the power bus and can last for several minutes. Cold crank generates a voltage dip, which can create drops of 6 to 9 volts below nominal battery voltage. The transient waveform can last from 1 to 10 seconds and can occur frequently, particularly in cold weather conditions. Warm crank is similar to cold crank, although not as extreme. The voltage will dip about 6 to 7 volts from nominal battery voltage. And the duration is typically shorter, but could last up to 10 seconds. And this condition occurs very often. Reverse battery applies a negative 12-volt potential across the vehicle's battery terminals. It can create a large energy event that is very damaging if not properly designed for. This condition doesn't occur very often, but it's commonly tested for up to 60 seconds. Ignition pulses occur continuously and are low energy pulses that last up to a few milliseconds. That are up to a few milliseconds wide and up to a few volts in amplitude. These pulses typically occur at lower frequencies, less than 500 hertz. Many inductive loads are present in every vehicle, and their switching behavior occurs very often. These transients can create moderate energy waveforms close to 300 volts, with durations that last for a few hundred microseconds. Although this list describes some of the more well-known transients that are considered, this is only a subset of the many transients that must be tested. Now that we have a basic understanding of some of the most common transient conditions, let's look at a few that can present significant design challenges for 12-volt modules. First, we'll look at start conditions, including cold crank and warm crank. Then we'll review reverse battery. And finally, we'll take a look at load dump. For each of these transient conditions, let's explore how the transient condition occurs, what the waveforms look like, and design considerations that a system designer must account for. To better understand start and cranking waveforms, let's first review a few points about lead-acid batteries. A 12-volt lead-acid battery has a chemistry that's very sensitive to outdoor temperatures. Lead-acid car batteries typically have a cold crank ampere rating described by CCA. In the US, the standard test for CCA occurs at 0 degree Fahrenheit, in which a load is applied for 30 seconds. To understand the impact of temperature on the battery, it's common to measure 60% less power at 0 degree Fahrenheit when compared to the power rating at standard room temperatures. In extreme cold, such as negative 20 degrees Fahrenheit, it can deliver 75% less power than at standard temperatures. It must also be considered that the vehicle's engine, including mechanical parts and engine oil, are also impacted by outdoor temperature. In a cold temperature condition, the engine will require more power to start. As an example, some engines require 200% or more power to start at 0 degree Fahrenheit as compared to 70 degree Fahrenheit. Cold crank describes when a vehicle starts during cold conditions. This means the vehicle battery and engine both have been subjected to cold temperature for a period of time. During cold crank, the starter draws a high current from the battery to start the engine, and the battery voltage can drop very low. For some vehicles, it may drop to 4 or 5 volts, and for other vehicles, it can reach levels as low as 3 volts. In the examples shown, the battery voltage drops quickly within a short time, such as 5 milliseconds. Then it holds at the low voltage for a short duration of about 15 milliseconds. Then the voltage eventually transitions back to the nominal battery voltage level over a duration that may last close to 10 seconds. For test waveforms, a low frequency sinusoid may also be injected to represent alternator noise. Warm crank describes when the vehicle starts during warm conditions. The profile for the waveform is very similar to cold crank. However, warm crank pulses are typically not as severe as cold crank. The voltage will not drop as low during the cold condition, and the pulse duration is typically shorter. The waveform shown shows the battery voltage dropping to 6 volts during a warm crank event, and with the lowest part of the pulse lasting 5 milliseconds. One example of a warm crank pulse condition is automotive start-stop, where the engine shuts down at a complete stop while the brake pedal is depressed. Then the engine restarts after the brake pedal is released. Many of the starting profile definitions and test waveforms are based on industry standards. ISO 16750-2 and ISO 7637-2 are two of the most commonly used specifications in the automotive industry. Both sets of standards define different starting profiles for both 12-volt and 24-volt vehicle systems. Each starting profile contains specific voltage levels, pulse durations, and other timing information specific to common cold crank and warm crank waveforms. The waveform shown here is taken from the ISO 16750-2 starting profile. The voltage levels shown for U sub S and U sub S6 are for specific start and crank waveforms. This is also true for the time period shown, such as the fall time designated as TF, and the different durations during the pulse, such as T6, T7, T8, and finally the final rise time. ISO 16750-2 also includes an injected sinusoid in its starting profile, while the other ISO standard 7637-2 does not. Many automotive OEMs use specifications that refer to one or both of these two ISO standards. They may also provide slight variations of these specs that pertain to their own unique requirements. Many vehicles require that certain functions continue operating even during various start conditions. A common example that we mentioned is engine start-stop. When the engine shuts off and turns back on, specific modules must continue functioning normally. For example, displays, radio, and audio modules may not be allowed to temporarily shut off during a start-stop transition. To meet these requirements, the system designer will add additional circuits that prevent low battery conditions from impacting their system. Consider the example shown for a display control module providing power to a display panel. The display control module must always provide a 12-volt supply rail to the display panel, even during start-stop. A buck boost converter can be used in this scenario to maintain proper output regulation at all times. In this way, display flicker and video dropouts are avoided. For systems that must tolerate various crank conditions, boost and buck boost converters are excellent choices. Both of these topologies offer high efficiency of 90% or more for large load currents, resulting in very low power dissipation. Wide VN converters are typically used that can operate down to 3 to 4 volts on the input. These devices must also operate up to 36 volts or higher to withstand other high voltage conditions. Reverse battery or reverse voltage describes a transient condition that occurs when the car battery is disconnected from the system and then reconnected with the battery polarity reversed. This condition can accidentally occur during routine maintenance or service of the vehicle. This creates a negative voltage of minus 12 volts across the loads and circuits that are typically supplied by the battery and alternator. As the figures show, or in the figures shown below, one of the ECU modules is connected correctly to the battery and the other is not. If you look closely at the polarity of the battery, it must match the polarity of the inputs to the ECU. Therefore, after examination, the figure on the left shows a battery that is correctly connected to the system. On the other hand, the figure on the right shows a battery that's not connected correctly. This shows a reverse battery condition. In the ECU circuits, we'll see negative 12 volts at their input connector. ISO 16750-2, section 4.7 describes a reverse voltage condition test and test method. The common test case described applies negative 14 volts for a nominal 12-volt system, and this voltage is applied for 60 seconds. After the reverse test is applied, after the reverse test voltage is applied, the battery is disconnected and then reconnected properly, and the system must be retested with correct polarity of positive 14 volts to ensure damage did not occur. When designing to protect against reverse battery, the designer must consider the reverse voltage capabilities of components in the system. For example, consider the buck converter circuit shown where VBAT is stepped down to a lower voltage VDD. Most ICs, including the buck converter and its loads, will only be rated for maximum reverse voltage of negative 0.3 to negative 0.4 volts. This is a common specification and limitation in many semiconductor ICs. Also, other passive components, such as input capacitors, are also sensitive to reverse polarity. While multi-layer ceramic caps can tolerate reverse voltage conditions, other chemistries such as aluminum electrolytic and tantalum electrolytic will not. These types of capacitors can suffer damage or degradation. In this circuit, the addition of a simple Schottky diode rated for the correct current will provide sufficient protection for the ICs and other polarity sensitive components. This example shows an effective and low-cost approach to providing reverse battery protection. A Schottky diode approach is good for low currents up to a few amperes max. The forward voltage drop, or VF, of the diode becomes a limiting factor at higher currents and higher temperatures, where it can dissipate power in excess of 1 watt. For higher currents, a different approach must be considered. Now consider a similar circuit having a larger load current. In this case, the buck converter pulls 4 amps from the battery input. For this circuit, we replace the discrete Schottky diode with a MOSFET, which includes the body diode of the FET. During normal operation, the MOSFET will be turned on continuously. The low on resistance of the FET greatly reduces the voltage drops and power losses across the switch. If a reverse battery condition occurs, the MOSFET will be kept in an off state, and its body diode will block reverse current while also protecting other components from reverse polarity. A MOSFET approach is good for larger currents of a few amperes and higher. Discrete and integrated approaches can be used depending on PCB space and cost requirements. For larger current applications, a smart diode controller is a very effective solution. It is usually small, low cost, and very efficient. Load dump describes a transient condition that occurs when the alternator is charging the battery and the connection to battery is lost while other loads remain on the alternator. As shown in the diagram, when the engine is running, the alternator is charging the battery while also providing power to other modules and circuit loads in the vehicle. When the battery connection is lost, the resulting large voltage transient can generate greater than 10 joules of energy, and it has a long duration that can last for nearly half a second. All circuits and loads connected to the alternator will be exposed to this large transient. In normal vehicle use, load dump does not occur very often. Conditions that could result in load dump transients often involve problematic connections to the battery. Some of these include a loose connection to the battery, in which the locations are indicated by the red circles shown. Corroded battery terminals, shown by the yellow circle, and faulty or damaged cabling, which is indicated by the blue circle. ISO 1675-2 and ISO 7637-2 specify automotive load dump for 12 and 24 volt systems. Both sets of standards define transient pulses for the cases of load dump, where there is no centralized suppression, as shown on the left-hand side, or with centralized suppression, as shown on the right-hand figure. In this example, the voltage transient is clamped to 35 volts to reduce the peak energy seen by the loads. Definitions for voltage levels, rise time, and pulse durations are provided in the ISO standards. Automotive OEMs typically reference one or both of these standards or modify the definitions per their unique system requirements. For systems that must ride through load dump and continue working, A transient voltage suppressor, or TVS, is widely used in many applications. A TVS is a special clamping diode that quickly suppresses voltages that exceed its breakdown rating. The device can shunt large amounts of current when breakdown voltage is exceeded. When the overvoltage event is removed, the TVS will then automatically reset. In 12-volt automotive systems, it's common to use TVS diodes that clamp voltages at less than 40 volts. In this example, 35 volts is chosen and is a good target for many systems. The components protected by the TVS must be rated at a voltage higher than the TVS max clamping specification. Transient voltage suppressor, or TVS, is one of the most popular load dump protection circuits. They come in many different sizes, voltages, currents, and energy ratings. The TVS minimum breakdown voltage should be higher than the intended battery operation range. This is the voltage at which the diode starts to break down and shunt current. Minimum breakdown specs of 24 volts are very common in automotive. The maximum clamp voltage is specified higher than breakdown voltage and pertains to the clamping ability at higher shunted currents. Specified values close to 35 volts are common. Finally, voltage ratings of protected ICs and components should exceed the TVS max clamp rating voltage by some safe voltage margin. This webinar provided background information on several critical automotive transients, including starting profiles such as cold crank and warm crank, reverse battery, and load dump. Each transient was reviewed to understand how they occur, how their test waveforms are specified, and how automotive system designers must account for them in their designs. Details on MPS automotive power products can be found at the link provided. And products targeting each of the transient conditions discussed today can also be found at the links below. Thank you for attending today, and we'll now open it up to Q&A.
Great. Thank you very much, Todd. A lot of good information today. If those of you who may have joined a little bit late, I did want to let you know that this session is recorded and we will have it available on demand, like all of our webinars, at monolithicpower.com/webinars. And we will send you out an email with a full recap here by the end of the week. All right. So we already have questions coming in, but for those of you that also have questions in mind, if you mouse over the Zoom webinar interface, you'll see a Q&A button. Click on that, type in your question, and we'll make sure to get it answered. But I see we have a couple already. The first one was, is there a preference or best practice for putting D1 before or after the TVS? And this one came in when you were on slide 17, Todd. So where you had that diagram there.
Yeah, let me back up. Let's see.
Oh, maybe it's slide 20.
Was it?
The numbering was maybe off.
Oh, slide 20.
This one? No, yeah, that's one.
Okay. Yeah, so this is often a subject of debate, and a lot of it comes down to the customer's system requirements. So, for example, this TVS that is shown here can clamp a very large pulse of current, and this circuit that's shown to the right may be one of several circuits that could be in parallel with this circuit. So there may be additional ones that connect to the protected battery at this point that's shown right here before D1. So D1 may be rated for lower current, like maybe a couple amps or something lower, to provide reverse protection for this buck converter and its loads. But it may not be enough current, or the rating of it may not be enough to survive a really bad load dump or other transient condition. So in this case, the designer may choose to put the reverse protection to the right of the TVS diode. Now, there are other applications where they may have a higher current reverse protection scheme where they may be using a MOSFET, like a P-channel FET or an N-channel FET ahead of the TVS. And in those cases, those parts may be rated for high enough voltage to, I'm sorry, high enough current to actually survive a large pulse of voltage and current. So it really comes down to the system design and what their key requirements are and what the different ratings are for the other protection components.
Great, thanks. And the second question on the same topic here was just, could you please highlight a bit more on the TVS diode selection? So if you had anything else to add beyond what we just covered.
Okay, yeah, I'll do my best. Yeah, so typically, the TVS is selected to meet the first thing is understanding the voltage input requirements for the system. So for example, if this system had to operate for like a double battery condition where 24 volts is applied, and this is expected to continue working properly, then this TVS needs to not have any impact on the system when that voltage is applied. So that's usually called, I believe it's called like a standoff voltage, where this component will tolerate up to 24 volts and it won't really sink any current. But then once you get slightly above that, then you start getting closer to what's called the breakdown voltage, or VBR. And that will be when this device starts to actively clamp, and it'll start shunting low amounts of current. And then as the current pulse or the over voltage condition gets larger and there's more current being shunted, then this clamping voltage can actually go up a few more additional volts. And that's usually what they call a maximum clamp voltage in the data sheet. And so V clamp will actually be the maximum specified voltage that this thing will clamp to for large amounts of current. So those are kind of the factors that you want to consider is, what is the normal range that the TVS needs to operate without impacting anything about the circuit? Where does it need to start clamping current? And then what's the absolute worst case condition where it's shunting a lot of current and you can't allow the clamping voltage to exceed some certain voltage, because that maximum clamping voltage needs to be below the rating of your buck converter or other circuits that are connected here. So I hopefully that provides some clarification.
Great, thanks. Next up, are there any standards emerging for line transients which are applicable for electric vehicles?
So I have to admit that I don't personally have a whole lot of electric vehicle customers that I directly call on, but I do know that there are always new automotive ISO standards and other standards that are being generated because of all the new requirements and challenges that are being experienced with the new electric vehicle designs. So yes, there are a set of standards and specs that are related to electric vehicles, and they may overlap some of the 12 volt and 24 volt systems in some areas, but then there's quite a few differences, since you don't have to worry about an engine and some of the other mechanical aspects of noise that get generated. And so the specs in the waveforms can be quite different, and they should be they should be clearly specified by the OEM. So whoever the car maker is will usually reference the correct standards in their design specs, and they'll make sure that their suppliers design to those specs and test to them.
Okay. The next one up was, let's see, you showed a P-channel MOSFET as a reverse voltage protection. There was a MOSFET control circuit. Are there chips designed just for that? And does MPS make them?
Okay, so I think they're referring to this circuit. And this is actually, this is an N channel. This should be an N channel symbol here, if I put it in here correctly. And basically, in this circuit, this circuit would need to have some kind of a gate voltage that's created that would be higher than battery. So a couple ways to do that would be by using a charge pump in this control circuit, or some type of a small boost converter that would always guarantee that the gate drive for this N channel is higher than the battery. There are also circuits similar to this where P channel FETs are used, and in those schemes, you don't need to have the higher gate voltage. You're able to pull the gate voltage low, or close to ground, to enable the P channel FET. The advantage of a circuit like this, which can often be realized with a smart diode controller, is that it can help reduce the size and cost of the solution, because a smart diode controller will be very integrated in a tiny little package, and it'll be able to drive an N channel FET, which is typically lower cost than a P channel FET. And you can usually get better power dissipation with an N channel FET. So I think I answered most of that question, but was there a part I left out, Kelly?
They also asked at the end that, did we have any specific chips available from MPS?
Oh, okay. We do. We have a part that's not released yet, but it's in development and starting to sample this quarter. So I would encourage you to reach out. You can send a message to Kelly, who's the host, or you can reach out to your local MPS salesperson and ask for the latest information on our smart diode controllers for automotive. I don't believe I can disclose the part number just yet because it's not released, but we'd be more than happy to show you what we have, as well as any test results we have and eval boards that are available. And I think the other question may have been related to power FETs, and currently we do not sell any type of P channel or N channel power FETs. Everything that we sell is integrated. So we do have some parts that have integrated FETs built into the power stage, but we don't sell discrete MOSFETs for automotive power applications at this time.
Okay, next up, how does 24 volt occur? That's all the detail we got in that one.
I'm sorry, how does 24 volts occur?
Yeah, I'm not sure.
So I'm not totally clear on that question, but I guess I'll refer back to this slide where 24 volts can occur in a 12 volt car system. 24 volts can occur when you get a jump start from a tow truck, because quite often they'll have a couple batteries that are stacked, and because they need to provide a lot of energy and current depending on the vehicle that they're trying to help start up. So it's common to see 24 volts used during a jump start application. Otherwise, there are 24 volt systems, which are typically different types of trucks, larger truck vehicles that usually have different requirements than the common passenger cars and the common passenger automobiles that use the 12 volt systems that we're talking about in these slides. So hopefully that helps. I'm not sure if I totally answered that question, but hopefully that at least provides some guidance and understand any comments to 24 volts and where they came from.
Okay, and the next one, we're going back to TVS. That's our hot topic of the day. That says the TVS also has to be able to handle the amount of energy, J, as well, correct? This will help size it, and then SMA versus SMC.
Yes, that is correct. Yeah. So when the engineer is designing uh, their their electronic module, they have a specification from their OEM customer. Like it could be, say, GM or Ford or Mercedes or whoever will provide them a spec telling them what type of load dump transient they need to withstand and for how long. And so based on that, they can then look at various suppliers of TVS diodes and try to size it correctly for the right clamping voltage that they need, the right amount of current that they think they need to shunt, and then there'll be a curve in there that shows the maximum energy that it can withstand for that period of time for the pulse duration. So those are all critical. And then the current and voltage rating, as well as the energy rating, will also dictate how large the package is. So SMA will be one of the smaller packages, and then you can get SMB, SMC, and so on. So the amount of energy that needs to be withstood will determine ultimately like how big your package needs to be.
Okay, thank you. Next, we have cold crank low level was shown with 3 volts. This is common. On previous projects, 5 volts or 6 volts was typical low limit. And then what is the technical reason of 3 volts, especially in combination to electric vehicles?
So okay, so there's 3 different questions there. So the first one, again, I'll go back to this, or I can even, I guess, reference this slide. So cold crank, the amount of current drawn from the battery in a cold condition is determined by the type of vehicle, the engine that it has and is trying to, that it's trying to start, the typical CCA ratings that are recommended with the battery used in that vehicle. And so there's a few different factors that the car maker has to consider, and then they will test and see what the worst case conditions are and how low that voltage is likely to drop, in certain temperature conditions. I think the other difference that we see is also in certain regions. We see, I don't know, like in the US, for example, a lot of the cold crank specifications tend to be more in the 4 or 4.5 volt range. Some of them are in 5 volt range. In Europe and sometimes in Asia, we see requirements that get even lower than that. Those might go down to 3.5 or 3 volts. So a lot of it has to do with the specific OEM and their vehicle design and the stringent requirements that they place on the designer to make sure that they have enough margin left over in the design so that they can meet the requirements all the time. So Kelly, there was the last part of that question. Could you repeat that?
Well, the last part was just what's the technical reason of 3 volt, especially in combination to electric vehicles. But if you go back to your slide that had the table on it, seemed like the question was primarily focused on these voltage, 3 volts versus 5 volts or 6 volts. And
right.
that seems like the primary emphasis of it.
Yeah, the main difference here is, when the engine is warmer and, and obviously under the hood, when the engine is warm, the battery will be warmer. during a warm crank condition, there will be less of a dip in the voltage when the vehicle is starting. So for cold crank, when it's cold, we're showing down to 3 volts here for the most extreme cases that we normally see. But there are cases where it's a little bit higher, like 4 or 4.5 volts, depending on the car maker. But then for warm crank, it is typically at least 2 to 3 volts higher. And the reason is because the battery doesn't have to work so hard to provide the energy needed by the engine to start up when it's warmer. And then for electric vehicles, I don't really have any information in here related to electric vehicles, but these waveforms here cover crank conditions that you will see in hybrid electric vehicles or plug-in electric vehicles, but they also pertain to just your standard gas engine vehicles today that also incorporate warm crank strategies and also have to attest to these crank conditions.
Okay, next up, how quickly can your FET, let's see if I read this, how quickly your FET control can switch off the FET to prevent the charge in the bulk cap from flowing back to the VBAT, as a diode can go to nanoseconds. How quickly is the solution with the FET can it be?
It is relatively fast. I mean, I don't have the exact I don't have the exact information that would allow me to tell you the exact timing or how quickly it could react. But these circuits, and especially these diode controllers, are designed to react quickly to protect against a reverse polarity condition. So, I mean, obviously, if they weren't fast enough, they probably wouldn't be very useful, and people wouldn't want to use them. They would try to use some of their other discrete approaches. But that's something I think we can look into more. And if we can get the information from the customer on that, we can provide more test data and waveforms back to them that shows how fast these parts react in that condition.
Great, thanks. And as you mentioned, if you do have follow-up or an inquiry, as Todd mentioned, you can ping me. Probably the easiest way is just info@monolithicpower.com, and I will get that email. So it's just info@monolithicpower.com, and we'll make sure to route that to the right person to make sure that it's addressed. Okay, back to TVS. You want the TVS to be bidirectional if it is exposed to reverse battery input. Seems like more of a statement than a question, but if you want to address that.
Let's see. So there are designs that will use bidirectional TVSs, for that situation, but then I would say most of the designs I see will actually rely on the fuse. So if for example, reverse battery condition occurs across the input terminals of this module, what will happen then is current will try to flow in the reverse direction through the TVS. And usually it's a very large slug of current, like it's a lot of energy in a very short time. And typically they will size that fuse so that it blows if that condition lasts for too long. So that's an approach that I see most often. And in that case, this diode will still help protect everything on this side. But if the reverse condition lasts for a long time and it's long enough to cause this fuse to blow, then that will help protect the TVS and the module. And then they will just have to go back and replace the fuse later after they figure out that they reversed the battery incorrectly. but there are systems, there are systems that use bi-directional TVSs as well. It just depends on the requirements, how much power is used by the module, what type of module it is, and when it needs to function. And so there are different strategies for sure, but this is one of the most common ones that I see at all of my customers.
Okay, and then next we have for newer EU car makers, they're cranking after every stop. Do you know what the difference is in doing so?
So yes, for the European car makers who are cranking after every stop, that's usually what we call the swarm crank, or it's a type of warm crank condition. And and again, the systems are designed so that when they come to a complete stop, like they're pressing on the brake, come to a complete stop, the engine will actually shut off. There's usually some small electric motors that may keep running to keep, like the air conditioning running and a few other things running. They want to keep, the radio playing continuously, keep the display showing continuously. And then once the person takes their foot off the brake, then the engine will start up again as they're preparing to accelerate or to go. In that condition, it's usually a warm engine condition, and the voltage will be something like what is shown here, where it drops to something maybe like in the 6 or 7 volt range, and then it returns back to nominal voltage. But that condition is what we call start stop, and it's a type of warm crank condition. There are vehicles that are designed to not allow start stop to occur until the engine actually reaches a certain temperature, because the other circuits are not able to continually run and uninterrupted if the voltage dips too low, like it would in a cold crank situation. So there are vehicles, where the design strategy is to make sure the engine is warm enough before they allow it to go into the situation where it allows for a start stop to start being employed, so that they can have better fuel economy, etc. But this is typical of what you see in a lot of the cars that have start stop.
Okay, and it looks like our last one is back to TVS.
It's a popular
So
circuit.
maybe that's the next thing we need to just do a full session on.
Maybe.
Let's see. I think the question is, will a 28 volt rated breakdown voltage TVS be destroyed if it will get to 35 volts?
It That's really a difficult question to answer without knowing the waveform of the load dump it's trying to clamp. Um, for example, you may see in a data sheet that a specific TVS diode will start clamping at 28 volts. So that's where when it'll start to shunt small amounts of current. But then as that energy pulse continues to get larger and it's a whole lot of current at that time, this device will start heating up. It will its ability to clamp the voltage will rise a little bit, and it may be somewhere close to 34 or 35 volts. But then it's a question of what's the duration of time that it's held in that condition, because if the energy is quite large and it's held in that condition for longer than the part is rated for from an energy standpoint, then certainly that part could fail. So that's where understanding the waveform and the duration and the energy involved is very critical. And then it just comes back to picking a device that's the right size that can handle the energy and be able to do that continuously. in a lot of the load dump tests, they also need to repeat the pulse several times, like within a certain time frame. So if you run a load dump test, for example, and the device fails after one pulse, you know that it's probably grossly undersized. If you run several pulses through it and it's okay for a few of the first pulses, but then it starts to fail or it gets damaged after a few, then it still may not be quite where it needs to be, and you still might have to bump it up again. But then, eventually you'll reach the right size and energy rating that would guarantee that it always works for your system.
Okay, I think that is the last of the questions. So a lot of good ones there, Todd, but thank you for the very thorough answers.
Yeah, well, thank you. Yeah, thanks for the questions. And if there's anything that we didn't answer or answer in the way that you intended the question, please feel free to let us know, or send information to Kelly, or you can include it in the chat here, and we'll try to respond after this session.
Great, thanks everyone. And at this point, we will conclude the session. Thanks again for attending, and we look forward to having you join us for the next ones as well. Have a good day, everyone.
Thank you, everyone.